Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the online lecture on control systems. Today we are going to start a new topic, which is root locus technique. This technique was proposed in 1948 by Evans. It's been more than 70 years and this is still one of the most useful techniques in control systems theory, and it's taught in all undergraduate control systems classes. Let's see what this is all about. Okay, so the essence of this control systems, I will just take the laser pointer here. So what is the essence of root locus? So the essence of root locus is that you have an open loop system, and then this open loop system, when you apply the controller to this system and close the loop. So by closing the loop, you mean that you are sensing the output of the system and you feeding back the sensed output of the system to the controller, so that controller can apply the corrective action on the plant. Okay, so what happens when we close the loop? So in the open loop, the transfer function from here to here is Cs into Gs, which is some transfer function. It will have some numerator polynomial and it will have some denominator polynomial. So both will be the polynomials of S. So if you denote the numerator by n of s and denote the denominator by d of s for this open loop transfer function, and when you close the loop, the closed loop transfer function, we have already discussed how to calculate this: direct path divided by 1 minus loop gain. So when you calculate this, then this turns out to be something like this. So what is interesting about this is, with respect to, if we compare it with this these two transfer functions, then numerator is same. So the numerator is same, and we have already discussed that the roots of the numerator are zeros of the system and roots of the denominator are poles of the system. So you can see that by applying feedback to an open loop system, the zeros of the system remain the same, whereas the poles of the system change their location. And sometimes so numerator and hence the zeros of the system remain the same, denominator and hence the poles change their location. Number of poles remain the same, but only the location of the pole changes. Root locus is the study of the change in pole locations in closed loop system with respect to open loop system. So we can with root locus we can determine that with respect to the poles here, what are the corresponding locations of these poles, which are roots of d of s plus n of s equals 0. So root means poles and locus means path. So root locus is basically the study of the path that is followed by the poles of the closed loop system with respect to the open loop poles. So next is that since C of S, the controller is designed by us, we know how if we know how the selection of C of S will affect the location of the closed loop poles, then we can design C of S to achieve our desirable closed loop pole locations. So this can only happen if we know how the selection of C of S will affect the location of closed loop pole, and that can only be done with the help of root locus. So root locus basically will help us in designing the controller to achieve the desirable closed loop system performance. And we have already discussed how system performance, like the transient performance and even the steady state, depends upon the pole locations. We can also add more poles and zeros through C of S. So there are some poles and zeros which belong to G of S, which is our plant that we want to control. Plant is usually given to us, so we don't have much to do about the natural dynamics of the plant, but we can add poles and zeros through C of S. Root locus provides us a graphical depiction of how exactly the closed loop pole location changes with respect to the change in the gain of the controller. So this is the motivation for root locus. Next we go into the basic definitions and notations regarding root locus. So root locus for the gain, well, we shall study the root locus for the gain 0 to infinity. We will what is the gain here? It will be clear when we actually go into studying the root locus in detail. It will be much clear at that point, but at right now you just think of it as a common like some DC gain value or some value that represents the magnitude of the control effort applied to the plant. So if you apply more control effort or less control effort, then what happens to the closed loop poles, that we will study. So control effort goes from 0 to infinity. And then the root locus from minus infinity to 0 is the complementary root locus. Since root locus is a mathematical technique, it covers all possibilities, but we are mostly concerned with physical systems, so we study only the part of it which is relevant to us and we can use in practical systems. Standard block diagram during the discussion of root locus shall be like this. So we have, instead of CS into GS, we shall have GS and HS, which does not make much of a difference other than that instead the numerator changes. Instead of CS into GS over 1 plus CS into GS, we have GS over 1 plus GS into HS. So this will be our standard block diagram that we shall be taking under consideration during the study of root locus. And if we go into further basic definitions and notations, we see that the open loop gain, this is GS into HS, we shall refer to it as open loop gain, and the open loop gain can be written as some constant K times G1 of S and H1 of S. So this is, like I said, this K is sort of like the multiplying factor. If you like multiply G1 and H1 with K, then that becomes G into H. So it basically depicts the magnitude in some sense. Closed loop poles are defined by 1 plus K into G1S H1S equals 0. So what is 1 plus K into G1 H1? This is basically this thing, 1 plus G of S into H of S. Remember that we have called G of S into H of S equal K times G1 of S times H1 of S. So so this, the roots of this equation will be the poles of closed loop system, and if you look at this G1 of S H1 of S, then from this equation, the closed loop pole equation, the G1 of S H1 of S is equal to minus 1 over K, where K goes from 0 to infinity. And if you take the magnitude on both sides, magnitude of minus 1 over K is just 1 over K, and on the left hand side you have magnitude of G1 of S H1 of S. This is called magnitude condition. And similarly we have angle condition, where angle of G1 of S H1 of S equals 2K plus 1 times pi, where K could be 0, 1, 2, 3, 4, 5 up to so on, any whole number. So these are the some basic definitions and notations of root locus, where we have magnitude condition and the angle condition, and we have defined some factor K, and we'll continue this discussion. Alright, so I understand if this is getting a little bit too mathematical too fast, but I promise you that by the time we are done with the topic of root locus, everything will be very clear to you. So far I just want to have a quick recap in the middle of this lecture, that so far we have just looked at the essence of root locus, and we have seen that when we close the loop with the system, for a control system, then the location of the zeros remain the same, but the location of the poles would change. And also we have seen that the C of S is something that is in our hands, so we design C of S. So if we know how the location of the pole changes in response to closing the loop and maybe increasing the gain or overall magnitude of C of S, then we can basically set the desired set the closed loop poles at the desired location and get our desired closed loop performance. We have been going through some basic notations and definitions. I have already conveyed to you that we are going to discuss this root locus for the gains of positive values only, because the negative value gains are complementary, so their root locus will be sort of like it's very similar to the root locus for this kind of gains, but its direction is reversed or something. So this would be the standard diagram for root locus study, and then we were discussing the magnitude condition and the angle condition. So what is the meaning of a magnitude condition? It basically, it's right now it does not have much meaning, but by the end of this root locus study, you will know the exact meaning of this magnitude condition. Right now it is just a mathematical expression of writing down this thing k1 into h1 as in the form of 1 over k, and this magnitude condition has been derived from this characteristic equation. This is the characteristic equation of the closed loop system. So in that sense, if this is the magnitude condition corresponding to the characteristic equation of the closed loop system, you can already understand that this magnitude condition is going to tell you something related to the closed loop poles and zeros. And similarly, this is the angle condition. The angle condition, I will go into a little bit more detail in the next slide, what the angle condition means and how we can use this angle condition. For now, you just have to just absorb the expression. Angle of g1 of s times h1 of s is equal to 2k plus 1 times pi, where k could be, if k is 0, then this is like pi. If k is 1, then this would be like 3 pi, and if k is 2, this would be 5 pi. So pi, 3 pi, 5 pi, 7 pi, 9 pi, and so on. And okay, so we next okay, so k into g1 of s h1 of s, since this is a transfer function, we can always write a transfer function. I just keep the k separate here, this k I just keep separate. So g1 of s h1 of s, this is a transfer function. I can always write a transfer function in terms of its poles and zeros. This is one way of writing a transfer function. Usually there is a numerator polynomial and denominator polynomial. Since every polynomial has its roots, so I can always factorize a polynomial in terms of its roots. So minus z1, minus z2, and up to so on minus zm are the roots of numerator polynomial. So I can write the numerator polynomial as s plus z1 multiplied by s plus z2 and so on. So the product of all the zeros. And similarly, denominator polynomial as product of all the poles. And this is one way of so the reason why I am talking about this way is because I want to rewrite the magnitude condition in terms of another format. So the magnitude of g1 of s and h1 of s is basically the product of magnitudes of s plus zi, where I goes from 1 to m, and divided by s plus pi, where I goes from 1 to n. So this is straightforward from this expression. If we take the k out from both sides and take magnitude on both sides, then magnitude of this complex number will be the ratio of the products of magnitudes of different complex numbers. Then this gives us, since magnitude condition states that this is equal to 1 over k, so k is just equal to this expression where poles come on the top and zeros go down. So we can calculate k from the magnitude condition, and if we know the poles and zeros of this transfer function, g1 of s, h1 of s, we can calculate the gain k. We will use this expression later on. And then there is angle condition. So angle condition can also be written in terms of poles and zeros. The total angle of this transfer function would be sum of all the angles due to zeros minus the sum of all the angles due to poles. Since poles are in denominator, their angles would be subtracted. If you know that the complex number can be written as in terms of its gain and argument means angle, so then you would know that any complex number that is in denominator, its gain remains so the gain would be like this, and the angle will become negative. Okay, so this angle is 2k plus 1 pi from the angle condition on the previous slide. And next we look into a little bit more detail of this angle condition. What is the practical meaning of this angle condition? So finding the angle at a test point, we look into this graph, which is the complex plane. All the poles and zeros of a system lie on a complex plane. So we are only interested in the open left half plane. So I have drawn some poles. So this is a pole, this is a pole, and this is a pole. This is a zero. So the system has like P1, P2, P3 and Z1, 3 poles and a zero. And if you take any test point S1 on the complex plane, let's say S1 is the test point, and if you want to find the angle at this point, so how can we use the angle condition to find the angle at the test point S1? So in order to do that, we have to draw vectors from every pole and every zero towards this test point. So from pole P1 I draw a vector towards the test point, from 0 I draw the vector towards the test point, from this pole I draw the vector towards the test point, and so on. And then I have to calculate the angle of this vector from the positive x-axis. So the angle of this vector from the positive x-axis, let's call it theta p1. Angle of this vector from the positive x-axis, let's call it theta z1. Let's call this angle theta p3 and this angle theta p2. These are all the angles, and now I am ready to apply my angle condition, which says that the angle of the g1 of s, h1 of s is sum of angles of all the zeros minus sum of angles of all the poles, and this will be equal to 2k plus 1 pi. And from above figure we have theta z1, and there's only one zero, so sum of all the angles due to zeros is only theta z1, and minus sum of angles due to all the poles is theta p1 plus theta p2 plus theta p3. We subtract the sum of angles due to all poles from the angle due to 0. We get some angle, we equate it equal to 2k plus 1 pi, and we'll get the value of k here, and then this is how you can apply the angle condition for any test point. Alright, so we will also use this angle condition in the future to find different angles, but until then you just hold on to this thought that to find the angle at any point. You just have to sum all the angles due to zeros and subtract with the sum of all the angles due to poles, and equate it equal to 2k plus 1 pi plus 1 pi, and then that is how you apply the angle condition. All the angles are with respect to positive x-axis, and that's an important point. And next we just move on to further notations. So this is another way of writing g1 of s into h1 of s. If you write it like a ratio of polynomials q of s over p of s, then what happens is that open loop poles, the open loop poles of this diagram, that would be the roots of p of s. So this is open loop transfer function. And remember that this is g1 of s, h1 of s is we have taken the gain k common out of it. That would not change the location of the open loop poles. So open loop poles will be the roots of this polynomial equal to 0, and then 1 plus k times g1 of s h1 of s is called the return difference. This is a capital K, as we have used before. Sorry about this typo here. This should have been the capital K that I've been using so far in this presentation. So again, this is a capital K as I have written here. So this is the right way to write down this K should be like this. So 1 plus k into g1 of s h1 of s is equal to 1 plus k into, so g1 of s h1 of s is equal to q over p. We put it equal to q over p. We take p as an LCM. When we take p as an LCM, it becomes p of s plus k times q of s divided by p of s. And then this basically gives us that the closed loop poles are the roots of p of s plus k times q of s equals 0. So this is what the closed loop poles are: p of s plus k times q of s equals 0, and the open loop poles are p of s equals 0. So you can see that the thing that we have called return difference, 1 plus k times g1 of s h1 of s, this we have called return difference. This return difference is quite interesting in a way that if you look at this expression, the poles of the return difference are the roots of p of s, which is also the open loop poles, and the zeros of this polynomial, the roots of this polynomial are zeros of the return difference. Zeros of the return difference are basically poles of the closed loop system. This closed loop system, the poles of this closed loop system are same as we have already discussed in the previous slide, that this equation equal to 0 gives us the poles of the closed loop system. And so that is same as putting this expression equal to 0. If we put this expression equal to 0, p of s will vanish, and we'll have this whole thing equal to 0 be the poles of the closed loop system. So return difference gives us poles of the return difference are open loop poles, and the zeros of the return difference are the closed loop poles. So once again, since this is very complex lecture, and but as I have promised that things will get easier as we move along. You will start to understand the meanings of many things that we have discussed today as we go through the root locus. But for now, I'll just say that I'll pause here. Why do I pause here? Because next we are going to discuss the 10 rules of root locus, and I want to have this topic for the fresh lecture and fresh video. Before we get to that, it is very important that you get a hold over these basic notations. If you get a hold over these basic notations that we have discussed today, then it will be easier to follow through with the 10 rules of root locus. Just to recap the lecture, I've discussed the what happens when we close the loop, and it is such that zeros of the open loop system and the closed loop system are the same, but the poles of the closed loop system have different location with respect to open loop system. How does the location change? That we will study, that we will know after we will have discussed the 10 rules of root locus. For now, we just finishing up with some motivation and notations. So the motivation is to be able to get a hold on the knowledge of how the closed loop poles move when we close the loop, and based on that knowledge we can adjust our controller to achieve desirable closed loop performance. And we can also add more poles and zeros. When we add poles and zeros in C of S, those are get added in the open loop transfer function as well as in the closed loop transfer function. But the difference is that in the open loop transfer function, the location of the pole is somewhere else, and in the closed loop transfer function the location is somewhere else. Graphical root locus gives us the graphical depiction of how the poles change their location with respect to the gain of the controller. And basic definitions, we have discussed that we shall be studying root locus for positive gain only, and this will be our diagram that we shall be discussing throughout the root locus. This is equivalent to the other diagram, but most of the textbooks and the literature uses this diagram, so it is easier for us to discuss this diagram during the root locus, so that when you study the literature or textbook you don't find any differences. Then we have basic notations, magnitude condition and angle condition. These are based on this closed loop characteristic equation. And we have defined the open loop transfer function in terms of gain k, that is the basically gain of the root locus. And then we have discussed in terms of poles and zeros, the same magnitude condition can be rewritten like this, and angle conditions can be written as sum of angles due to zeros minus sum of angles due to poles equals 2k plus 1 into pi. And we have looked at some graphical depiction, how to calculate an angle at a test point using the angle condition. And then we have some finally we have defined the important quantity called return difference. Return difference is interesting because it gives us poles and poles of the open loop system as well as the poles of the closed loop system. And with that I finish this discussion, and let me know if you have any questions. Thank you for attending this lecture.